Good evening, and thanks for joining us. To get ready for tonight, I reflected on how much exposure to statistics I had had growing up, and honestly, it wasn't much. As I've grown older, I've realized more and more how important statistical concepts are for my students to learn, which is why I'm so glad that we have Diane Broberg and Karl-Heinz Haas here with us tonight. My name is Mike Houston, and I'm the moderator for this event. I teach algebra and calculus near Pittsburgh, where I use TI technology to make tough-to-teach, tough-to-learn concepts accessible to all my students. And let me introduce Diane and Karl-Heinz. Diane has been teaching mathematics for over 30 years. Many of those years in New York State, she moved to Missouri to join the Mary Institute and St. Louis County Day School, where she leads a pre-K through 12 math and computer science department. She enjoys the opportunity to impact students as young as 4 years old while helping to shape the math and coding curriculums. She served on writing teams for text instruments and has led workshops throughout the country. Making math come alive for teachers and students keeps her creative. Outside of math, she's an avid runner and baker. So Diane, it's great to have you with us tonight.
I'm excited to be here. It'll be fun.
And Karl-Heinz taught science and mathematics in Germany and in New Jersey for nearly 10 years and worked as an administrator in several school districts in roles ranging from the math science supervisor to director of curriculum, as well as assistant superintendent. After moving to Florida, he is now at the Pines School in Hobie Sound, Florida, where he teaches advanced placement and honors levels classes in physics and statistics. As a TCube national instructor, Karl-Heinz has presented workshops at conferences and TIPD programs around the nation. He is especially proud of adding a newly designed STEM lab course to the Pine Schools program that integrates many of the TI STEM lessons and Innovator Hub and TI Innovator Rover activities. So Karl-Heinz, it's really great to have you with us as well.
Thanks, Michael.
All right, Diane, would you mind talking through our agenda?
Sure. Well, we've done our welcomes and introductions, so you've gotten that part already done. So tonight we're going to talk a little bit about statistics across the curriculum. Where does it fit in between our middle school grades and our high school grades? Then we've got a few activities we'd like to talk about that we're going to look a little bit at TI-84. We'll also look at Nspire activities that could be worked. And at the end, I understand we have a webinar drawing, which means if you stay around till the end, you have the opportunity to get a graphing calculator.
Thanks so much, Diane. And Karl-Heinz is going to talk through our expected outcomes.
Yes, Michael. Our expected outcomes for the evening are that we can explore statistical concepts using some of the TI technology. And also that we can visualize data to help students make those connections between the concepts and the data. Another expected outcome for the evening is that we connect real-life data to statistical concepts, and lastly, to navigate the curriculum to add statistical activities throughout the existing mathematics teaching.
Thanks so much, Karl-Heinz.
Yeah.
So tonight we're expecting a large crowd, so your audio is muted. Feel free to ask any questions of Diane or Karl-Heinz using that Q&A window on the right side of your screen, and we'll also be using the chat window to send general messages. As a reminder, the session is being recorded, and we'll provide a link to the event certificate of attendance at the conclusion of the webinar. All right, Diane, you should have control. Feel free to share your screen.
Thank you. Looks like I need to make it full screen here. Let me see if I can get that to be full screen. Sometimes, well, let me ask you a question as we're thinking about this. Hey, Karl-Heinz, like, why do we need to know statistics? It seems like we talk about it a lot. It's something we hear, but why do we really need to know statistics?
Well, why don't we start by looking at a graphical representation of some data, and maybe the participants can even help us in that. The chart you're looking at is from the Georgia Department of Health and goes back to the beginning of the COVID-19 pandemic. And it shows in very pretty colors with dates across the bottom, the COVID data for 5 selected counties in Georgia with the greatest number of confirmed cases. So it's probably somewhat difficult to see on this chart in this presentation. But I was wondering if you notice anything as you look across the bottom and look across the date, or maybe even look at the colors of the bars that represent the different counties.
Well, it looks to me like the data, it decreased, like COVID cases definitely went down as you look from left to right.
Yeah, right.
It's definitely declining.
Right, very interesting to look at that. But I wonder if you can you take us to the next screen? If we look at that, well, we made 2 little changes. Actually, once it was pointed out to the Georgia Department of Health in one of those well-known Twitter storms that the data was kind of poorly represented. They fixed one thing, which is the dates were all out of order.
Wow, look at that. If I go back, they did
the dates.
Yeah, isn't that interesting? The old data was not in the correct date order.
And secondly, if you take another look, you see that the colors of the counties, that the bars are also all over the place in the first chart, and now in the second one, all of a sudden they rearranged it in the right order. And what's obviously not happening here is that there is no trend as the first one seemed to imply. So it would certainly be helpful if our students had some understanding of how to read data. It's already presented for them in chart form in a nice little bar graph, but how do you read it? And then maybe we should look at another graph. If you happen to have that third slide ready for us. Oh, okay. How about this one? So we have, again, Georgia, cases per 100,000. And if I look at the map of the state representing all the counties, and then I look at the one on the right, also representing cases per 100,000 residents, it looks pretty much the same. So the numbers, I don't think the numbers changed much. There are these little red areas with the highest numbers, the darker blue, the lighter blue. Is there anything that you notice?
Well, again, it is interesting because they look about the same, so there wasn't a lot of changes. But look at the numbers you circled for me. Like on the left-hand graph, it was 29, almost 3,000 to 40, to partway through 4,000. And on the right-hand side, the minimum value is 37,000. So that's pretty significant.
Yeah, I think if you look at the scale that they applied, the only one that stayed the same is the white, which means no cases. Unfortunately, none of the counties in both cases has 0 cases, and they clearly played with the scale there just a little bit. So I think hope that these examples kind of make the case for us to look for examples, look for ways to integrate statistical literacy throughout the curriculum. And I know you wanted to talk a little bit about statistic standards in the Common Core and state standards throughout the country. So why don't you go ahead?
Yeah, well, one thing I've noticed as over the past about, I would say 5 to 10 years, there's been a lot of change in statistics. There's been a lot of change in what teachers are teaching and what's being required of teachers. And so some of this came out of the Common Core, some of this has come out from state standards. But if we look through this, all of a sudden back in middle school, these are as young as 6th grade standards. We're supposed to be talking about how do you talk about variability? How do we summarize data? How do we use graphical distributions to allow students to begin to see data and grapple with data? And we, even in middle school, this is still a 7th or 8th grade standard, is they need to be able to look at bivariate data. So that means they need to be looking at, not necessarily cause and cause and effect relationships, but they need to start looking at correlation. Is there a relationship between two variables? I keep teasing my friends who are teaching AP statistics and tell them, hey, if it keeps going like it is, pretty soon we're going to be out of a job. There'll be no AP statistics course because we're going to realize that statistics is so important that it's being taught in our middle schools, that it's being integrated into our Algebra 1 curriculums, our Algebra 2 curriculums.
Right.
Geometry is a great place to do a whole bunch of probability. And if schools start doing what they should be doing, maybe all of a sudden you aren't going to be teaching AP statistics anymore, and neither am I, because it's going to be done. And I think it would be a great service to our students to start moving statistics down. And so we as math teachers have to figure out, how are we going to fit it in? How does it become part of our curriculum now? What can we let go of? Or how can we incorporate statistics in to some of our current topics?
Yeah, I think that's probably one of the questions some of our participants will be asking. Can I teach some of the more traditional algebra or geometry topics using statistical applications?
Yeah, I think it's a real question. So one of the first activities that our middle school students did at school had to do with M&Ms. And I shared this activity with you. And we want to let's talk about that one a little bit. This was at the beginning of 7th grade. They were just beginning to talk about fractions, decimals, and the relationships between them. Are you okay if I look at that activity with you?
Yeah, absolutely. Why don't you do you want to share the?
Yeah. Let's see if we can find it on our Nspire here. So first thing our students did is we gave them each a package of M&Ms. It's a pretty good time of year to do it.
Yeah, absolutely. And I see you had quite a few bags of M&Ms that you were sharing there. So if you want to scroll over all the way to the left so that participants can see. So we have all the colors in there, and I assume that every row represents one bag.
It did.
Okay. So just by looking at that, I can tell already that the numbers are not very evenly distributed. So some students got 3 blue and others got 6. Somebody got 16 green. Another student only got 7 green. So clearly there's something going on. Not very regularly and fairly distributed, it seems.
Yeah, so it was an interesting question. So that was a big thing to try to figure out is what was going on.
So how do we represent the data now? You're showing it there on the Nspire, and I think if you scroll a little bit further to the right, you'll see that I see that you have the totals in there. So
I do.
So you have in all your samples, you had a total of 382. What color is that? Blue?
I had 382 blues.
Oh,
yeah,
good.
I was able to use the sum feature. I really like that.
So let's think about a good way to represent those color distributions. One of the ways middle school students and then also still the high school students are asked to represent that would be in form of a box plot.
Yeah.
So if you want to move to the next screen, but we'll see we have this nice feature on the Nspire here. We can put all 6 colors, a box plot for each of the 6 colors on top of each other and compare them to each other. And in explaining the box plot, if you could just hover over the end of one of them, the lower end or the lower end, you see there's a number 3. And then if you go to the end of that line, you see a number popping up there, hard for me to see.
That's Q1. Here, Matt, let's do the green.
Q3, and the 3 and in green, I have 6.5 there as the Q1. So what do these numbers represent in the box plot, really? What about that middle line? Do we know anything about that middle line in each of the boxes? Or the median? So that's the middle value. in each of them. And I saw a question that just popped up in the chat. Can you hover over that brown circle there and what it represents? So that's
Pretty cool
30.
one.
So that only the brown ones, the brown colors seem to have that that dot that's kind of on the outside there. That's a great feature of the Nspire, that it shows us the outliers. A lot of our students have some kind of a not very specific understanding of what outliers are. Very often, if they see a point a little bit to the left or the right, what do they see? It's an outlier. For them, anything that's a little bit out of the ordinary, that's an outlier. But we have a much more specific definition here. And the numbers that I see popping up there in the box plot are what we call the 5-number summary. So you see those 5 numbers that describe the data. In response to a question or a comment that just came up, I was surprised too that that's the only outline in our M&Ms. The blue ones have just a much bigger range. So what is that range there? So you have a low of, can you go to the bottom of it again? So that's 3. Then we have the upper quartile, the 3rd quartile at 20, and all the way up to 30 M&Ms. So the 5 numbers would be that the lowest value, the minimum, the 3. Then we have the 1st quartile at 7. We have the medium at 12, the median at 12. Oh, in this one, it's 9. We have 20, the 3rd quartile, and then the last quartile at 30. I think that's it. See.
Yeah.
One of the things that the students have trouble understanding in the beginning is that each of those 4 segments, if you want, each of these 4 segments of the graph, from Q3 to the maximum, from Q3 to the median, from the median to Q1, and from Q1 to the lowest, the minimum value, actually includes an equal number of data points. Although the right part of the blue seems so much bigger than the left part, they both have the same number of data points in them. That's hence the definition of the median at that value right there. Right, so we have these 4 quartiles that divide the data up. The brown one, as mentioned before, is the only one that has that outlier there. And maybe when we talk about the penny activity, one of the penny activities in a little bit, we can get into a more technical definition of what that outlier is. I think one more thing we wanted to show in our M&M activity.
Hey, before we do that, Karl-Heinz, can I ask you a question? So one of the things I was thinking about is like, what questions, if you're a middle school teacher, what kind of questions should we be asking our students when they see this data? If we want them to understand statistics, like what are the type of questions? Do we ask them like,
do we know how many data points are in each of those box plots? Do we know that? Could we go back to our chart? Because the yellow one seems such a small little box plot, and the color part, the 2 middle quartiles are much smaller. The maximum is much lower for the yellow part. So are there fewer of them? Are there fewer samples? What does this really represent?
That's a good question. I think another question that's kind of interesting for students is like, which 2 distributions have the exact same middle value? Are there 2 distributions that are the most similar?
Are there any?
Most similar?
I don't know. What do you think? The red and the green ones?
Maybe. They at least have a similar center. You know, do we have students look at these things and say, hey, compare two distributions. What can you tell me about the people's yellow M&Ms versus people's red M&Ms? I mean, those are two kind of really interesting distributions.
Yeah, and I'm trying to watch some of the comments and questions that are coming up. One of them was are we more likely to get one color over the other?
Yeah, are we? That's a really interesting question. What do you think? I'm not sure there's an answer. Are we more likely?
Well, we seem to have a lot of blues there, right? So it seems like all of the bags seem to have had more blue than they had yellow or orange.
Right, but isn't it an interesting question to say to students, is there a probability that you will get more yellow than blue? And I think for a middle schooler, that's a really pretty rich question.
Yeah.
For them to consider, like, is it unusual? You know, would you be really surprised if you got more yellow M&Ms than blue M&Ms?
Right.
Pretty question for students to begin to think about. Hey, but we had one other thing we wanted to show them about these M&Ms.
More things we want.
Yeah.
So one of the things we did, and I think maybe an interesting function to share with the participants before we get to the pie chart. If you go back to the table to page 1.1, so one of the things we did, we do have the totals in there. So out of those bags that we sampled, you had a total of 82 blue, 323 green ones. The red, the green, the blue seem to be high in the totals. But if we go over one or two more columns, actually go back one. So here's what we did, and not everybody may be familiar with that particular function in the Nspire. So we have a total of 382 times the color blue, 199 times the color orange. Now, how do we turn that into a list short of typing blue 382 times and then orange 199 times, etc., because we have a total of way over 1,000 M&Ms there. So there's this little function that we put in column I that takes a frequency table, the frequency table being the totals for each color, and turns them into a list. The two variables that we have to enter is color and totals. Those are our frequencies, and then the variable that goes with each of the frequencies. So all we had to enter was, we chose that functionality, frequency and frequency table to list. We put color, we put totals, and in the column I, the expanded, we now have all, I don't know, 1,000, several values that is probably too long a list to really check. But what did we do now with that list?
So we took that list over here to the next page, and this is my expanded. So this actually graphs it as a pie chart. So another way for students to look at data, this is where, again, one of the things that we were hoping the 7th graders got to think about is because now we get percentages. And how do they then tie in? What is the relationship between that graph and their percentages? And so they were surprised that, yes, a yellow is our smallest, okay, with all about 7%, or 106 yellow M&Ms.
Right.
So that was about a quarter. But that surprised students when they first saw that, because it looked like from the bar chart that we should have, the box and whisker plot, that we should have that many more.
Yeah, and so that was a quick way to use that functionality of the Nspire to turn that frequency table of how many of each we had into an expanded list, and then get the percentages right there. If you hover over one of the colors, you can see that we have the number of cases, 323 green, which represents 21%. etc., of all the other colors.
Yeah.
I think that there's a whole lot of good questions in there, a whole lot of statistical data analysis that can be done with these numbers.
And I'll tell you what then, Carol Hines, what I do in my AP stats class, because they like M&Ms just as much as the 7th graders do.
Yeah.
Take
Right.
this a very similar activity, and I expand it to use the chi-square test. Because if you look at the M&Ms website, they will tell you often the percentages of each
Right.
color, and based on those percentages, although that's getting harder and harder to find,
Yeah.
based on those percentages, I do try to do a chi-square test. So interesting, we can take an activity, same activity, we could do it in 7th grade. We could probably do it as young as 4th grade, looking at pie charts and beginning to think about pie charts, all the way up to our seniors and an AP statistics class.
Yeah, and for just a few little bags, you can have even a bar chart for the younger ones. You can just make a little histogram of the 6 colors and a couple of bags. Yeah,
kind of cool activity. Right now with Halloween, stock up all of you, because you can do some pretty cool activities.
Yeah.
Okay. So
and if any of you are concerned, I think Diane only used the peanut-free M&Ms.
I did. That was really important at school. Okay, so hey, we have a second activity. We're going to talk a little bit about pennies. We have 2 different cool penny activities you did with your classes. I'll still drive them on the calculator, but let's see what we can do with them. I think it was, let's see, whoops, I got my data here. Whoops, I got the wrong one. Hold on.
Yeah.
Here we go. So I got ahead of ourselves. Tell them what you did.
So it was a pretty straightforward sampling activity, actually. Over my years of teaching AP statistics now at the Pine School, I have amassed quite a bit of a penny collection with the help of donations from students and parents and colleagues. So I probably have about 2,600 pennies of all different ages in my collection. So what we did was, for this activity, the students took 30 samples. I think there's 30 trials. Could you scroll down and remind me? I think there are 30 total trials. And in each of these trials, the students sampled 30 pennies and then just put them on a scale and measured the total mass of those pennies. Because we wanted to be able to find the mass of 1 penny. So we said, okay, instead of weighing 30 of them or 100 of them, why don't we do just quick samples of 30 each and take that total, and we simply divide it by 30 to get the mass of 1 penny. Now, as you can already see from that list in column C, those masses, although they look pretty close, they are not identical. So they are actually, as expected, I think, there's something called sampling variability. So not all the pennies in that big bin of my pennies are exactly the same mass. I don't know how difficult it would be to find out what the masses really are or should be for a penny. Well, not that difficult at all. Turns out that we can get that data from the US Mint and compare it. You are actually going to take me there, aren't you?
I am. And I did it.
So the weight of the penny, there is actually a list available, and it shows that over the years, the composition of the penny, the size, the total mass of the penny changed dramatically. And there's actually 1 year in there, somebody commented, interesting trend. Yeah, they're getting smaller and lighter. There's 1 interesting year in there, and somebody in the audience may remember, may have heard about that. I don't think anybody was alive. But in 1943, there were only zinc-coated steel pennies available. The 1943 steel penny, because copper was needed in the war effort during that year. And then in 44, 46, they came back and they had some copper back in it. Now the penny since October of 82, if you look at that list, is copper plated zinc. And I think it is still worth more. The metal is still worth more than the actual penny. Now what you see there is right now, the penny of the most recent, the 82 through the present, they are 2.5 grams. And before that, before 82, they were 3.11 grams. There's a totally different composition. The chemistry teachers can probably help us out there, see how that the different masses are affected. But going back to our Nspire activity, so now you may see that, yeah, they are close to 2.5, 2.6, 2.56, et cetera, et cetera. So we have 30 samples here. Let's go back to our trusty little box plot and see how we can represent this data. Now we already talked about box plots. What you see now is, again, they are dots. What looks like there are actually 5 of these outliers. The second one from the right there, that's actually 2 different values. Yeah, you actually managed to show both values by hovering carefully. So there are 5 outliers in this data. So there's 2.65, and go to the one on the very right. So there was one sample that was an average of 2.6788 grams. So that's an average weight of 30 pennies. So just to remind everybody what the data points represent. Each point represents the average mass of 1 penny taken from a sample of 30. So total mass of 30 divided by 30 gives us these data points. The median, let's see what the median is, I'm wondering. 2.57, so that's heavier. That's more massive than 2.5 that it should be. What about the light ones? So the minimum, the outlier 2.5. So that's kind of interesting that the minimum value that we have in all samples is actually a tiny bit higher than the 2.5 grams that it should be for all of them. So we actually have kind of a trend that's a little, it's a little bit something to think about. What do you think is the reason for most of all of our data points actually being to the right of the actual mass or average mass for a penny according to the US Mint?
Well, when did you start collecting them?
What's that?
When did you say you started collecting them?
Well, I started collecting them around 2014.
Oh, so I was going to say you've just been teaching for so long, Karl-Heinz, that you probably started collecting them in 82. Maybe I shouldn't say that.
Maybe they're just dirty, somebody said. And
that's a good one.
It's a good idea. Okay, yeah. Saying, they're dirty. Did I at any point imply that all the pennies that I collected since 2014 were 2014 or newer? I don't think I said that, did I?
No.
So what could be the reason for those higher mass averages? I could say
Did you have older pennies in it?
My penny, I'm just watching. Yep, my pennies are old. Somebody just said my pen. Yes, my pennies are, at least some of my pennies are old. That's for sure. And if we have time, Michael, at the end, I want to go back to the question: how did I keep a record of all the years of all my pennies? Because I'm not exaggerating. I actually have over 2,600 pennies now in the collection. So if we have the time, we'll talk about how that can be done. It involves child labor. So we have all these pennies. We have the outliers. can talk about the students, when I do the activity, the students do not have that chart that we shared before. So they don't necessarily know that pre-1982 pennies were slightly heavier. So they don't have that information. But so before we get to the analysis of how, where we can see that, how we can see that, let's take a look at the dot plot, if you don't mind, on the next slide. So there's a different representation, and you see scale matters. That's something our students are often struggling with. At first, it seems like there's not much difference. But when we use a scale that ranges from 2.5 to 2.7, all of a sudden the differences are much more noticeable.
Mm-hmm.
And we see that the average, that median line that we saw in the box plot is actually right around where we have that maximum number of points there. So the actual median is at 2.57, right along that 2.58 line. Right, so what does that mean? Well, it really doesn't mean much more than that half of the samples that we had are below 2.57 and the other half of samples are above 2.57. And the other two lines that I put in for us to talk about are the upper and lower quartile. And it shows that the upper quartile, that value there, right there, unfortunately, the word average and the number is right above that. The upper shows us where outliers begin, right? So it's that line based on the definition of outliers, any value above that number 2.6 is an outlier. And the same is true on the other side. There's one actually, the top one of the two there at the line labeled lower. The top one is actually inside. It's not an outlier. The bottom one is an outlier. So there are two outliers, just like the box plot showed us. Now, the question we're asking, where did I get these numbers from? Before we were talking a little bit about how to define outliers, because the students are so quick to say if a point's a little bit outside, well, that's an outlier. That's too far out there. It's an outlier. But how did we arrive at these numbers? And I think on the next page, so the next, maybe one more. Here we go, one more over. This is actually then a very technical definition of the outliers. So for those of you who teach high school classes, it's probably a topic beyond middle school statistics topics, but if you're teaching high school classes, we have this thing called the interquartile range, which is the difference between the upper and the lower quartile. And we multiply that difference by 1.5 and add it to the upper quartile and subtract it from the lower quartile. Those are the two numbers you see there. Q1 minus IQR times 1.5 and Q3 plus IQR times 1.5. That's how I got these two now, how we got these two numbers, 2.51 and 2.62. So there are actual outliers in there, and they are outliers according to our definition here, Q1 minus and Q3 plus IQR times 1.5. So, but I think, Diane, I'm right I'm correct in assuming that's probably beyond the middle school curriculum.
That is a little bit. Hey, but can we show them something? I
Yeah.
really like the other representation of it. You did the other thing with pennies that was actually pretty, like, maybe a little bit more dynamic. Look at this one for a second. So,
Okay.
how much you did here?
Okay, so in this particular activity, I actually just had the students weigh or find the mass of individual pennies. And what you see is, I think, a total of 50 pennies.
Yep.
And in column A, we just have the individual mass of penny 1, penny 2, penny 3, etc., etc. In column B, we simply have the number 1 through 50. And then the third column represents the total mass, one added to the next, to the next one, to the previous one, to the previous one. So we're just adding the masses. So I'm showing basically adding 1 penny at a time. And hopefully nobody's paying attention to the fact right now that there are already 3 pennies showing on the screen that have a 3 in the mass. So
Kids don't pay attention.
we're probably about to give away the secret of why we have these strange average masses in there. But here you can see, so tell me what you did there, what you see there.
I love this graph. This looks like, according to your graph right here, every single penny falls on that line. They're all the exact same weight because as you add them up, like every student would obviously see they all have to be the exact same weight. Because if not, it wouldn't be linear. I'm positive that has to be. That's what students are going to think. That's pretty cool.
Yeah, and I think when we talked about,
penny,
yeah, go ahead. I just noticed something there about that 2.57.
Oh, at 2.57, that's the number we got on the last page.
So what does the slope really represent in this graph? So for every penny we go over on the x-axis, we go up by 2.57 grams on the y-axis, right? So the slope, is that what I'm seeing there?
That is.
So the slope of our graph is actually representative of the average masses there.
It is. That's what we got in the last one too. But can I show them the real kicker of this whole thing? The thing that got me so excited? Karl Heinz then showed me this graph. Like the stats part of me was jumping up and down. What a beautiful graph that's bimodal. All of a sudden now students can see, like, here are the pennies that we should, like, where are the pennies that are between 1982 and now? They're all right here. Look, there's some that are less than the correct, they're less than the weight. Like we're getting gypped out on these pennies down here. And then we can see how many pennies actually did Karl Heinz have in the sample. But there's 1 there, 2, 3, 4, 5, 6, 7, 8. There are 9 pennies.
So almost 20% of my pennies in this particular sample were actually older than 1982.
Yeah.
Right,
which
so
is kind of interesting.
So by graphing it this way, I guess we noticed 2 things now, and you were pointing that out. Now all of a sudden, the lighter ones, the less massive, they all do seem to be centered around the 2.5, where they should be, and the 9, the small sample there, they're not centered around the 3.11, but they're very close. Most of them are very close to that number that they should be 3.1 grams per penny. So what we didn't see in our dot plot or our box plot earlier. And now we can see it. Now we can explain why were all our averages in those samples above 2.5. Here we can see it in a sample of 50 pennies. Now we all of a sudden have a bimodal distribution. And as long as I had this activity, I have to admit I didn't even notice that until you pointed it out when we changed the scale of the mass axis there. That was pretty cool.
Yeah, so I think that's a really good point that you just talked about, is that one of the things we do try to teach actually in AP statistics is what things do you never see when you are looking at a box plot? We get back to our box plot. What do we not see from a box plot that we can see with a histogram. And that's one of the important things. And when we talk about students understanding statistics, this is a key topic that students have to understand, that sometimes if I am a person that's trying to quote, sometimes we talk about how do you lie with statistics? Well, here, I can kind of lie with statistics in terms of what would I like students to see.
Right.
When I actually graph it as a histogram, we get extra data, we get extra information that we didn't
Right.
have otherwise.
Right.
And that's pretty significant for us.
Yeah, and it's bimodal data is not that easy to come at. I mean, there's plenty of it out there, I'm sure, but this is a fairly simple activity. If you have a large enough sample of pennies, if you can somehow get your hands on some older ones in your overall sample, you can get some nice bimodal distribution and sampling. And like I said, this is only 50 pennies, so as long as you have enough of the 1982 pennies in there, you should be all right.
Yeah, it's an interesting set of data. Thanks for sharing that one. I really like that set of data.
So
Yeah.
you wanted to take a look at a couple of middle school topics, the relationship between a couple of variables. Maybe switch over to the to the 84.
Yeah. Hey, Mike, can you put this question out for our participants? See what they think. If you have
There he is.
anything that has a relationship here, this is your time to check it out with us. What do you think has a relationship?
And although the time limit that Michael has set is 5 minutes, we're not going to give you 5 minutes to check 1, 2, or more things on that list.
And while we're doing this, I'm going to stop sharing my screen. Carl Hines is going to share his so he can work on the 84.
All right. Did you?
Oh, wait a second.
It's not yet.
Oh, where did my thing go? I said stop sharing.
You stopped sharing, so.
Yeah, go. Hold on just a second.
I think I got it. I got you. I got it. All right, so let me switch us over to the 84 emulator, and there we are. You can see my screen now with the 84 emulator on it?
I can.
Okay, great.
So let's ask you all. Let's see, Mike, can you check us? Can you tell us what they chose? I see an A and E for sure.
We probably need to give Michael a minute or two to get the data together. So we want to get us started on the 84 activity, because you had some great data there.
So we looked at some data. So if you go back and let's show them the data we came up with. In using the 84, a little bit different. 84, we started and I collected some data with my class, and actually Carl Hines collected data with his class. And we actually, it was kind of cool. He and I put our data together. He's in Florida, I'm in St. Louis. We put our data together. And so the first thing we did is we created 2 lists. And so Carl Hines is going to have to hit second and stat clock for us just to turn it on for a minute. Let's show the 2, we graphed actually 2 sets of data here. And if he hits graph right now, let's see
you want both plots on? Is that what you're saying?
Let's on for a second. And
okay.
So if we look at this, we notice these 2 graphs are pretty similar to each other. And so what we did is those graphs that are red, all the red dots are the students that Carl Hines and I have in class. And so then my students and I were talking, and we're like, well, is this concept of wingspan and height, is that important? Are we people that are square people? Or we had this concept, could you be sometimes they told me, are you a tall rectangle or are you a short rectangle? And so if you'll notice, we added 3 more pieces to our 3 more data points that are all solely in blue.
So what you're saying is those 3 blue squares, those 3 data points are only in one of our lists. Is that what
they're only in one of our lists? And the question I asked my students, and I would ask all of you participants, what's true about all three of the data points that are only in blue? Give a quick answer in the chat. What do you think? What's true of all three people who are in blue? They have a positive residual. That's a really good answer. What does it mean? Really hard concept for students. My students took a test on this yesterday. What does it mean to have a positive residual? What does that person look like? What does their height look like versus their wingspan? I should probably have told you that our explanatory variable is height. Our response variable is wingspan. What can you tell me about all the people who are only in blue?
Yeah, I saw they have large, not only do they have a positive residual, they also seem to have larger residuals.
That's a really good one.
Than most of the other, I don't want to say all of the other, but certainly most of the other members of our group.
Yeah.
Anything else come to mind as you're looking at that? Taller than wingspan, or now I see wingspan is higher than their height. They're all above the line of best fit. They're all at the right end of the data. All very good comments.
So that means, think about what that means. And one of the things that we really need to do as stats teachers is help our students put everything in context. Yes, I agree that they're above the line. They're all a little bit to the right. They are all have positive residuals. Those are great comments. But to put those in context, if I was actually looking at those people, I would be looking at 3 tall people, but are they really out a long way outside of our data? It looks like we have 2 people that are exactly the same height. There's one below the line and one above the line.
Yeah.
And so they're not too much, still, it's not extrapolation, it's not too far out, but all 3 of those people would be tall, but they have extremely large wingspans. And that puts it in context for students. We then actually talk about.
So if I hear you correctly, you're saying this person here has the same height or is as tall as this person, but this person has a much higher, a much wider wingspan.
If they do, that is very, very true. They do have someone said they might be good basketball players. I will tell you, one of them is a very good basketball player.
Yeah, actually, I think that is actually the very good I'm trying to think. I think that is the good basketball player.
That is the good basketball player. That not right above. Oh, wait, someone else said. Wait, go back. Someone else said.
Wait a second. Somebody was just saying Michael Phelps. His arms are too long.
Yes, and one of those does happen to be Michael Phelps. We will tell you those 3 people are Michael Phelps, who is considered to be an unusual swimmer. And part of the reason was because of his unusual wingspan. The second one is Michael Jordan. And Michael Jordan also had an unusual wingspan for his height. He is the point right there that Carl Heinz just pointed to. And the third one, some of you may not remember the person. His nickname was the Albatross. His name was Michael Gross. He also was a swimmer who was quite good. And so these 3 people have unusual things. Now, let me ask you a question. What will those 3 points do to our data? Do they improve or do they improve our correlation, or do they make our correlation worse? That's an interesting question. So let's do that. Let's do a line of best fit. So let's hit stat.
Okay.
And let's go over to calculate.
Okay.
Let's do a linear regression. Now, you can either do 4 or 8, completely up to you. This time I think we have to do, what was it, height?
We height and weight. Okay, so I have to go to my lists.
Oh, yes, to get them this time, you have to go to your list.
List.
And go down to height, which is number 7.
And then I go to my, okay.
Yeah, is going to be wing.
And go up. So that would be wing.
Yeah.
Get that one in there.
Yeah, and now go down. Let's store the regression this time. Go down to there. Let's store it in Y2. So if you hit alpha and trace, remember that shortcut.
Trace.
And let's do Y2.
Okay.
Let's calculate.
Okay.
Let's hit enter.
Okay, so we have.
Oh, wait a second, Carl. You don't have your diagnostics. Hey, can we show participants how to find the diagnostics? I
Oh,
get
could we
this
please?
all the time. So
If you could tell me how to do that.
Yep, let's get mode.
Okay.
And if you go down to says stat diagnostics, go down a little bit further. It's one of those blue ones.
Okay.
There you go. Turn that on. Students have a lot of trouble with this one also. If you turn that on, hit enter, now hit second and quit.
Okay.
Now what I like is use your up arrow.
So are we?
Go up arrow twice. Just your up arrow. It should get back. Up arrow one more. Hit enter. That's our great cut and paste. Do it again.
Two. Ah.
Oh, now you got it. So this gives us an R value. Now let's graph it. Let's see what happened to the line.
Okay. So would you like me to graph both of them or?
Let's leave them both on there. They're two different colors
Okay.
right now. Hit graph. So those 3 points were actually pretty significant. We would say that those 3 points actually are pretty influential points because they changed our regression line so much.
So they increased the slope, it seems to me, right?
It did increase the slope. It increased the slope, and it also, interesting, it decreased the y-intercept.
Right. Yes.
We would have had to know our correlation coefficients to figure out what kind of input it had. So that's kind of what we're looking at. So hey, I will tell you all the answer to the question. The only one of these things that does not have a relationship is nose length and ear length. I thought it was a really cool activity I did with students. And then, we forgot to put, this is the problem, all of you participants. We did not put Michael Houston. He was feeling bad. We left him out of one of our 3 Michaels. So now all of a sudden he's going to tell us because of that, we have to stop. Hey, before I stop though, let me tell you all, in your participant materials for today, you will get all of these lists. Carl Hines and I have created them both in Nspire files, and we have created them as TI-84 files. So all of these files, all of these lists, all these activities are set for you all to work with.
And Michael has already taken control back, and we'll turn it back to you, Michael.
Thanks so much, Diane and Carl Hines. As promised, as we're wrapping up, we're giving away to one lucky winner a TI graphing calculator this week. And tonight's lucky winner is Karen Grozik. So Karen, congratulations. We'll be in touch over email in the next couple of days here to get some information from you, mainly which calculator you'd like to receive. So congratulations. To receive a certificate of attendance, go ahead and click the link in the chat window. Also listed is a link for the documents from tonight, as promised. And if these links aren't working for any reason for you, just go ahead and hang tight. In a couple days, you're automatically going to get a follow-up email. And in that follow-up email will be a link to the recording so you can watch this at your own pace, a link to the certificate, and a link for the documents as well. And if you're watching this on demand, go ahead and copy this link into your favorite browser to receive your certificate. If you have any questions for us specifically, feel free to get a hold of us at 1-800-TI-CARES or send us an email, ti-cares@ti.com. We'd love to hear from you. I see that Carl Hines just put his email in the chat window if you need to get a hold of him for any reason.
Feel free to contact me at any time.
And when you leave the webinar tonight, a brief survey will automatically appear in your browser. Your feedback really does guide us as we plan future online events. So if there's something that you'd like to see, feel free to let us know. We hope you really share your thoughts in the post-webinar survey. Huge thanks to Carl Hines and Diane. Thanks so much for everything you guys shared tonight. We really appreciate it.
You're quite welcome, Mike. This is great. Really enjoyed it.
And thanks so much for everyone for joining us. We hope to see you back online next week. Have a great night.